Okay, so in the last video we set up these two equations. We have the charge as a function of time, capital Q, which is our amplitude, cosine omega t plus phi, and then we take the derivative of that to find the current, negative Q omega, that comes out in front, sine of omega t plus phi. Now, as I said before, I want to keep the last video a little short, so now let me show you what the new energy equation looks like. Recall that the energy inside of the capacitor is going to be Q squared over 2C, okay? So now that charge is changing in time, so I'm going to substitute this charge right here into that equation. So now I get that the energy inside the capacitor is going to be capital Q squared over 2C multiplied by the cosine squared of omega t plus phi. Okay? Q squared over 2C, that capital Q is the amplitude of the charge, cosine squared omega t plus phi. So all I did was plug this guy into this guy. Now I've got to do the exact same thing for the magnetic field. Okay? The magnetic field, the energy inside of the inductor, we said before, was 1/2 Li squared. So now I've got to put this I right here down in here into the energy inside of the magnetic field. So that energy inside the magnetic field is now going to be 1/2 L, let me make sure I got everything here, omega squared, Q squared, sine squared of omega t plus phi, sine squared, okay? So I substituted the current down in here into the energy inside of the magnetic field, 1/2 L omega squared Q squared sine squared omega t plus phi. Okay? Now we don't really like that right now, and we remind ourselves that omega, the angular frequency for the LC circuit, was equal to 1 over the square root of LC. So that means that right here I've got 1 over LC on that omega squared term. So I can substitute that, make this thing look a little bit nicer and more like the energy inside the capacitor, and I get Q squared over 2C sine squared of omega t plus phi. Okay? So that's what we have right now. Okay? Energy in the capacitor, energy inside of the inductor. We made a really big assumption when we did this. I'm also realizing that my tie is still tucked in because I was erasing stuff, so I'm going to pull that out right now. Try to get a little bit of humor into these videos. We made a really big assumption when we did this problem. We assumed that the energy would not change in time. The total energy would not change. If, however, we introduce a resistor into the system, we all know that resistors give off heat, so energy is going to be lost. So this is the damped oscillation in LRC circuits. So, same exact thing, we're going to have an inductor, we're going to have the capacitor, but now we throw a resistor in there. Your brain should think of it this way. Think about the spring block system that we did last year. Now we've added friction to the system. We did that before. When we added friction to the system, we needed the whole energy to die off. So we need it to oscillate, and we need the total energy to die off. So we're going to need two functions to solve the following differential equation, okay? You should remember what that is. I'm going to dramatically pause right now. Okay, we need the sine cosine function to create the oscillations, and then we need the E function to make this thing die off, okay? So we have the same U total. We have the same U total is going to be equal to Li squared over 2 plus Q squared over 2C. This thing is getting real wobbly right now. We'll make it work. Okay. Now when I take the derivative of this, I'm going to lose energy. So when I do du dt, we're going to lose energy, and we're going to do that inside the capacitor. That's the power inside the capacitor. Minus I squared times R. Minus I squared times R. So when you take the time derivative of the total energy, it's not equal to 0 anymore. Time is going to be a factor, and the more time this goes, more energy is going to be lost inside of that resistor. So now I have a du dt of negative I squared R. Notice it's minus because we're losing energy. Let's go through and do all that time derivative business that we did in the last video. Li di dt Okay, so that's me taking the time derivative right here again, doing it exactly the same as the last video. Take the time derivative right here, and we're going to have plus q over c dq dt. Only now it's equal to minus I squared r because of the energy lost. So this is a new differential equation that we have to solve. Notice how complicated this differential equation is because I've got the I squared term right there. Okay? So I'm going to rewrite this whole thing to try to make it look a little bit nicer. The differential equation we have to solve is L d squared q dt squared. Again, I'm using the exact same trick that I'm taking the time derivative of I, and that's going to be the same as taking the second derivative of the charge, plus q over c plus r dq dt is equal to 0. Okay? So that's the differential equation that I have to solve right now. That's not exactly very nice, is it? It's not exactly a nice differential equation. Thankfully, the answer is pretty straightforward. Okay? I'm not expecting you guys to do this. I'm not expecting you to know what's going on here. I will just give you the solution. Again, we need it to oscillate, so there has to be a sine or cosine component. And we need it to decay, so there's going to be an e term for the decay. I'm going to flip over to the next board in order to finish this up, so please pause the video if you need the rest of this. Okay? We work with what we can, right? Okay. So, the solution for the charge as a function of time, capital Q, e to the minus RT over 2L. So that's e raised to the minus RT over 2L, cosine of omega prime t plus phi. Cosine of omega prime t plus phi. And I need to define omega prime. Omega prime is defined as the square root of omega squared, so that's the angular frequency squared, minus r over 2L, the quantity squared. Okay? So this is your charge as a function of time, capital Q the amplitude, e to the minus RT over 2L. That's going to give us the decay, that's the energy loss. The cosine gives us the oscillation, cosine omega prime t plus phi. And then I have to define omega prime as the square root of omega squared, that's the old angular frequency, minus r over 2L, the quantity squared. Again, I'm not going to ask you guys to solve this on your own. It's a little complicated. Differential equations are hard, but you should know how to use these equations if I give you a problem where you are referring to certain times.